Good morning, good afternoon, and good evening, everybody. It is my pleasure to introduce you to computational methods session of Philomania 2020. My name is Małgorzata O'Reilly. I am a researcher in a discipline of mathematics at University of Tasmania, but I'm sitting remotely at home chairing this session. Let me introduce the first speaker in the session, Frederick Madsen from Fred Hutchinson Cancer Research Center, strongly represented actually in this session. So there will be more than one talk represented by speakers from this center. So let's, without further ado, let's start. Thank you.
Great, thank you very much. Great to see some friends in the audience. And let's see, let me see if I can scooch this around somehow. Well, anyway, that's that. And thank you very much for the organizers. I appreciate it. I know it's a ton of work organizing something like this, so I'm really grateful. So I'm just going to give a spin of what we've been up to with variational Bayes phylogenetic inference and talk about where we want this to go. So our goal really is to rebuild Bayesian phylogenetics from the ground up. And the people that we're working with are as follows. I want to highlight especially Matthew Fourmont, who's from Australia, Sydney, who's done a lot of really important work in our efforts here. Gian Suchard. Jiang was Mark's PhD student or a postdoc and is now a faculty member. Christian Svanpool, who's Kiwi in Alexei Drummond's lab. Jian Zhang, who was in my group, but has moved on to his own faculty position in China. And folks from my group, Song, who has a recorded talk, Michael, who will be speaking later, and then Andy and Hassan, who have made great contributions as well. So just to motivate Bayesian phylogenetics and describe a little bit about what it is, just to remind you, we have some observed sequences that we're conditioning on. Maybe there's also some additional information about where these sequences were sampled or when they were sampled. And we want to infer a posterior distribution on trees, which I think of as being, what are all the set of explanations for this data that are credible? And what is the posterior weight that we assign to them? So to what extent do we think that each one of these reconstructions are true? Why do we want to do this? I'll just very briefly motivate with a relevant example. So here we have a bunch of tips that are sampled at various times for SARS-CoV-2 viruses. We want to reconstruct the phylogeny and also the transmission patterns. So these transition patterns here are just marked as colors, and we're interested in, for instance, whether transmissions from country to country. And this histogram is pretty important. This is showing that most of the nodes of this tree have very low posterior support. On the other hand, what if we only care about transmission from country to country? So, and then these authors did something quite clever. This is, I forgot to describe, this is a paper from Philippe Lemay and company. We can sample just one of these sequences and we can pick one of these sequences, and then for every sample in the posterior, we can go back, and look at when the colors change. And for each one of those, we can record that as a single jaggedy line going back in time like this and across space. And even if we have very low certainty about any particular tree, we can still get interesting conclusions about how this virus passed from country to country to country to country to its final place where it's sampled in Switzerland. So I feel like this is the story of Bayesian phylogenetics. Even if we don't know exactly what the tree is, we can integrate it out and we can learn interesting things. So we love Bayesian phylogenetics. Why am I giving this talk? I think that there's two major issues hindering Bayesian phylogenetics right now. One is that specialized packages create this isolated research area, and also that it scales badly and we cannot update inferences with new data. So this first one, what I mean by that is just to say that models are coded in a specialized package such as BEAST, where you have to write Java, or a bespoke probabilistic programming language. And I have tons of respect for the works of this, but it is sort of at odds with the modern frameworks. So here, for instance, what if we want to have a neural network in our epidemiological model? Are we going to code it up in Beast? Are we going to code it up in RevBayes? I guess, maybe. But in general, inference these days is happening in these big general purpose frameworks, TensorFlow and PyTorch. So I'm not going to really talk much about this, but maybe you can see Matthew's talk and follow the work of Christian Swamppool, where they're trying to integrate phylogenetic models into these general purpose inferential frameworks. And of course, for this work, we're using Beagle algorithms, including gradient work from Xiang and Mark and others. But mostly I'm going to be talking about this problem, that Bayesian phylogenetics scales badly, and we cannot update inferences with new data. So of course, what we'd really like to be able to do is Bayesian phylogenetics for real-time epidemic control. I'll remind you how Bayesian phylogenetics works right now, that we do Markov chain Monte Carlo. And for MCMC, we make a proposal in which we select a random subtree, it gets cut off, moved somewhere else, and glued somewhere else. So this could be a SPR move or an NNI move, if you know what these things are. So this proposal gets accepted or rejected according to the Metropolis-Hastings ratio. And then our sample is just taken from this Markov chain Monte Carlo process with the idea that if we run it for a long time, the posterior probability of a given topology is proportional to the number of times we visit that tree. Just to make it clear, public service announcement, MCMC is not equivalent to Bayesian inference. MCMC is one way to draw an approximate sample from a posterior. And it has this unfortunate thing that if we change the model or the data, we have to get a new sample. So we have worked on updating posterior samples. So if you might have seen these papers from a few years back. And these things do work, but still it's sort of fragile. It's not a super robust thing. I also acknowledge that there's some recent work where people have eliminated burn-in using a distance-based method to augment a tree with new sequences. And I think this is all important work. But I really feel, I mean, having worked on this for a while, I really feel like just the sample is the problem. That samples are sort of fragile. So the question is, can we throw out tree sampling altogether and do something else? Before I dive into what that is, I'd like to establish some terminology. So if we have a probability distribution on a discrete space, here it's just the numbers 0 through 5. The support of the distribution is just the number of positions that are basically assigned a non-zero weight. So I think of Bayesian phylogenetic inference as having two tasks. One is finding the support of the tree topology distribution. Another is inferring distributions on continuous parameters. So I think of this like this. We have our topological support, which is what are the trees that get non-zero weight in our posterior? And then on top of that, there's some continuous stuff that happens. There's what is the posterior weight that we assign to each of these trees? And then what are posteriors on tree parameters, such as branch length? And then on top of this, there's also another thing that's not shown in this diagram, which are like the model hyperparameters. So just to write it down, random walk is not an efficient way of finding topological support. MCMC algorithms need to find the same tree again and again using random walk in order to assess their probability. So it's not really a good search, right, walking around randomly. Also, random walk MCMC is not a modern and efficient way for inferring distributions of continuous parameters. So modern methods use gradients. So if you're looking to maximize something, you follow the multidimensional derivative, aka gradient, to the maximum. And if you are sampling, you can use advanced algorithms such as Hamiltonian Monte Carlo. So MCMC finds the topological support and infers the distributions on continuous parameters simultaneously. But we don't have to do that. We could find the trees once and then perform parameter and probability estimation on them. And so we did this in a rather naive way. What we did was design an algorithm where we started at lots of random starting trees and then did a hill climbing search to find a local minimum. And then sort of fanned out from those local minima, trying to find the ensemble of high probability trees in the posterior. And then we did posterior weight estimation using a really simple thing, maximum likelihood branch lengths. And even though this is sort of like a crazy, silly, naive thing to do, it works pretty okay. And you can see, for instance, these figures showing reasonable correlation between what we estimate up here and then Mr. Bayes. But I acknowledge this cannot scale. Tree posteriors are big, and there's no way that we can do anything on all of those possible trees. So rather than finding entire trees, let's find tree building blocks. So, and then we can do continuous parameter estimation. So what do I mean by building blocks? So I mean things like this. So let's imagine we're coming down a tree and we encounter a split between two subtrees, one with taxa set U, which might be the mammals, V, that might be the reptiles. A building block is a statement that says something like, if we have this situation, then we're going to allow this U group to split into the monotremes and the non-monotreme mammals. So we can think of this as a continuous probability distribution, or we can just think we're going to allow this particular subsplit to happen. And this generalizes work by Hood and Drummond and Largett, and we placed it into a Bayesian network context. This is work by Chen Zhang in my group. So before we talk a little bit more about that, I just want to say we can build many trees with a small set of these building blocks. So we did an experiment recently with 1,500 Ebola virus sequences, and we just used 42,000 conditional probabilities. And our tree support was over 10 to the 241, which is a very big number. And of course, we're never going to be able to do anything on 10 to the 241 trees, but maybe we can do something on these building blocks that will allow us to do inference on a rather large set of trees. So how do we use these building blocks in practice? We think of them as conditional probability distributions. So imagine that you have given me these conditional probability distributions, and you also give me a tree like this, and you want me to evaluate the probability of this, this tree given all of these conditional probability distributions. So I just multiply it out using the rules of conditional probability and assuming some conditional independence. So first, we just have what is the probability of this fundamental split, then we condition on it. So we move over here, and then we say, what is the probability that C is the next thing to split off? And then we condition on this substructure, and we say, what is the probability that D is the next thing to split off, and so on and so forth. So this is an approximation, basically. We're not able to express every single probability distribution on tree topologies. And how good is this approximation? Well, let's imagine, I'm going to make a cartoon, which actually has a real result in it, but this is just a cartoon. Imagine we have a space that's parameterized by the number of tree structures. So our target phylogenetic posterior is one point in that space. It's a vector where the ith entry is what is the posterior weight assigned to the ith phylogenetic tree. So what I've just described to you is a subspace. So the set of probability distributions that can be parameterized in this form is a subspace. And we're sort of curious how long this distance is. So how close can we get using these variational approximations? I don't know about in Australia, but in New Zealand, they always say, how long is a piece of string? So like, what is our absolute measure for this, this distance? And so what we did is we ran Mr. Bayes in a relatively conservative way, saying that we want our ASDSF to be less than 0.01. And then we saw how far is that Monte Carlo approximation if we project it to its very closest variational approximation? Do we get closer or farther away from the target phylogenetic posterior? And it turns out we actually get a lot closer. And that, I think, tells us that this model has good inductive biases. And so this is just a cartoon, but if you want to look at the table, take a look at our paper. So we don't, of course, want to be using a Markov-Chain Monte Carlo. That's the whole point here. We want to avoid that. So let's estimate this variational approximation directly. So how do we estimate continuous parameters of a posterior? Well, we can have a distribution of interest, which here I'm just imagining is a one-dimensional distribution. And then we have our variational approximation, which has some parameters associated with it. And we just fit our variational approximation to this distribution of interest. So to make it clear, if we're thinking about distributions on topologies, this is our variational distribution. If we assign the parameters of this variational distribution are these conditional probabilities, and we can fit this to the true tree posterior. So we also, of course, need to be able to parameterize branch length, and I'm not going to talk about that. But that's another thing that we need to do. But it's a little bit more standard, so I'm not going to talk about it. And so the way that it works is you can take your current approximation here. This is an approximation on the tree topology and other parameters such as branch lengths in the branch lengths. And then we basically want to do gradient descent or gradient ascent to get us to the true posterior. And a standard way to do this is to take your current approximation, sample under it to get a collection of points. In this case, these are trees. That allows us to form a gradient. And then that allows us to take gradient steps so that we're moving our approximation to the true posterior distribution. So, so now we've sort of shifted a little bit. So in the first part of the talk where I said we did this naive thing, we were doing something like this. We were trying to find the trees and then looking for continuous parameters associated with those trees. But we shifted now to thinking about what is this building block support, and then what are these conditional probability distributions that make our topological posterior, and we also take variational distributions on the branch lengths. And so this works with generic gradient estimators, and they work okay. So here we have a plot that shows the Kale divergence of the ground truth, and here we have Markov chain Monte Carlo. And here are variational algorithms that are going down reasonably quickly. But the thing is, this is in terms of iterations. This is not the same thing as wall clock time. And each of these iterations is more expensive than the MCMC iterations. And so that's sort of promising that it basically works, but this is not yet really a time competitive algorithm. And so to win, we really need to develop methods that are specialized to the tree case. And really one of the problems is that gradients are highly stochastic and expensive. And so these gradients, for instance, so if this is a tree sample, we're not going to sample in a given tree, it's going to have a small subset of all of these building blocks. And we want to form a gradient in terms of the probability of these building blocks. So that's sort of the stochasticity problem. And they're expensive. They're linear time, but that's still sort of too expensive. And so what do we do when we're faced with a problem? We think about what Felsenstein did. So Felsenstein, of course, developed the pruning algorithm. And so we need to be inspired by this pruning algorithm to make a faster algorithm. So for pruning, what one does is you have your data, you have your tree, and you do a calculation in which you summarize basically all that you need to know about subtrees in these vectors called partial likelihood vectors. So here we have a partial likelihood vector that summarizes everything down here called P, and a partial likelihood vector for everything up here that's called R. And so if we want to optimize what's happening in terms of this branch here, we don't need to recompute everything happening on the tree. All we need to do is do a very, very fast operation that has to do with this vector, and this branch length. So this is sort of nice, and this is used, of course, by all of our maximum likelihood and Bayesian phylogenetic methods. But for us, we are looking at a distribution of trees, and this branch is basically parameterized in terms of a model where we don't know exactly what the tree is. So how do we handle that? Well, in recent work, we've come up with a way of dynamically integrating out this tree uncertainty and forming partial likelihood vectors that marginalize out the tree uncertainty here. So now this is sort of what is the average partial likelihood vector that is pointing this way, and the average partial likelihood vector that is going this way, and then we can do local optimization. If you want to hear more about that, Sung has a recorded talk But the spoiler is that this enables locally constant time updates and gives us a pretty good estimate of the conditional splitting probabilities. And it is an approximation, but we are working on slightly more expensive but still scalable algorithms that are less of an approximation. So there's also an outstanding problem that I want to be clear that we have not solved this problem, which is how do we find the support of these building blocks? How do we find the ensemble of building blocks that we're going to allow to have non-zero probability? Because once we have that set, then we can use our nice continuous gradient algorithms and so on. And so I believe that this generalized pruning algorithm that I talked about in the previous slide is sufficiently accurate to be able to infer the tree structure support in much the same way that we do tree exploration in maximum likelihood phylogenetic inference, where we try just swapping out branches and seeing if that's a good tree. Here we can swap out branches and see if that's a useful addition to our set of building blocks. So this we're not done with this. This is proposed work. We also have been working on Bayesian supertree methods, which Michael's going to be talking about in this session. But the idea is that in the future, we would like to be able to use online algorithms, i.e. online in the algorithmic sense, using existing tree posterior and extending it with a single tree at a time. We want to be able to use these in parallel and then merge all the results so that this tree is going to be close to each of its sort of extended trees. So see Michael's talk for that. And so just very briefly to wrap back up, step back a little bit. So people have done amazing things with MCMC and algorithmically and so on. But there's these really sort of strict rules that keep us from being very flexible about what we're allowed to do. So for instance, it's difficult to design algorithms that learn along the way. Integrating the previous runs is challenging. And so there's just a lot of rules that we have to follow if we're going to be getting a true estimate of the posterior distribution. But I contrast that with maximum likelihood phylogenetics, where just like anything goes. You can pick someone up and throw them down or bonk them on the head with a chair. And it doesn't matter what you do. If you get the highest likelihood tree, you win. And that's great. So I'd like to make Bayesian phylogenetics more like maximum likelihood in that regard. I'd like to start with approximate heuristics and then refine. I'd like no holds barred search for building blocks of topological support. And that's not a random search, that's some sort of smart directed search. I'd like to be able to use local gradient-based methods for these continuous parameters. I'd like to reuse the support of the tree building blocks between runs. And then if we really love MCMC, we can use these tools to guide MCMC, because that's going to be a really great proposal distribution. Or we can do importance sampling. And I also would love to enable inference between a fixed tree analysis and a full Bayes analysis. Okay, I think I'm running out of time. But just to be clear, we're not yet ready to replace MCMC. So maybe that makes you grumpy, like we haven't done anything. But I remind you that MCMC has had 25 years to develop. So with that, I will say thanks again to our collaborators and also who are currently working on this, also Vladimir, Minin, and Chris Whidden, who did a lot of great work with us before. If this interests you, drop me a line ASAP. There's some funding deadlines that are in the next few weeks. If you want to talk about just the pre-proposal part. So I'll say thank you very much to the organizers and thanks to our funders.
Thank you very much, Fred. We have time for a couple of questions, if someone would like to ask now.
I've got a question. That was a great talk. I really enjoyed it, Eric. I know you don't want to talk about branch lengths, but I wondered if you could give just a quick, brief overview of what you mean, how you deal with the branch length problem.
Yeah. So. No, it's not like I'm opposed to talk about them. It's just it's a little bit less novel than topological parameterization, and so it's also a sort of thing where you are parameterizing branch lengths in terms of tree substructures. So the simpler thing that you could imagine doing, which is not what we do, is that every split gets its own variational distribution on branch lengths. You say, we're going to fit a distribution per split for what the branch lengths for that split are. So we found that not to be sufficiently flexible. And so what we ended up doing is using a slightly richer parameterization where you sort of said, we have this split and then some other sort of other related splits that are nearby, and then we use that to parameterize the branch length distribution. Does that answer your question?
Yeah, thanks for that. That's good.
Thank you. Are there any other questions?
Yeah, I have actually a question. Could you talk a little bit about the gradient of your topologies? You know, I mean, if you do variational Bayes, right, you want to move from your made-up distribution to the target. And you had a slide there where you talked about the gradient. And how do you do the gradient of your topologies?
Yes. So the point to the thing that makes all of this work is that, yes, and that's sort of like, that was the thing that was the sticker for a long time. We want to be able to do this gradient descent, but how do you take the derivative of something discrete? And the point is that we're actually not taking the gradient of a discrete thing. What we're doing is the parameterization is in terms of these conditional probabilities. And so this is a continuous probability distribution. No, it's a distribution that's continuously parameterized on a discrete set of things. So let's imagine that there's just two possible resolutions that we allow. There's this one and there's like another one. Maybe D comes out first. So we're interested in estimating what is the probability that C comes out first or D comes out first. And so those are things for which we can take gradients, these conditional probabilities. So we're parameterizing a distribution on a discrete set in terms of continuous parameters, and those are things for which we can take derivatives. Does that make sense?
Yeah, I have to think a little bit because it seems to be kind of a high dimensional problem, right? I mean, the gradient, you know, in this space seems to me kind of rather tricky, but I'm happy to read about it.
It is high dimensional. I have, there's a few blog posts that I've written as well as the papers. The papers are a little terse, but if you have any questions, just drop me a line.
Thanks.
Okay, thank you very much. Thanks to Frederick Madsen for this very interesting talk, and I'm sure we'll have more questions later on during our discussion session. May I introduce the second speaker for our session on computational methods, that is Michael Carter, also from Fred Hutchinson Cancer Research Center. Thank
Wonderful.
you.
Thank you for having me. Let me bring up my slides. Wonderful. All right. So that was an excellent introduction to sort of the entire field of variational Bayesian inference from Eric, which makes my job quite a bit easier. So you'll notice some familiar concepts in this talk. But I want to start from the beginning. So I want to work with the building blocks of tree topologies. So I'll be only working with the topologies. So if I refer to trees, I'll only be referring to the topologies from here on out. But we'll be defining it as a rooted graph with the root up at the top showing the shared ancestry of its tips. And just for sort of a notational ease, we have the tips down here in these circles, and we'll have our nodes in the graph represented here by these squares. So the motivation behind this whole thing is, what if you have two fragments and you believe they're from a larger tree? So suppose you had a tree topology that you didn't know, but you imagined that if you trimmed out tip D, if you pruned out tip D, you would get this tree on the left. And if you trimmed out tip B, you would get this tree on the right. And with those trees in hand, could you then reassemble the larger tree? So in order to be able to describe the various methods for accomplishing this, I want to take a number of different ways of specifying our trees. So earlier on, I described it in terms of tips and nodes and the edges that join them. That's a traditional way of specifying a tree. And there are a couple different ways which will feature useful terminology. So let's zoom in on a couple of those. So we define a clade as a set of tips. So we'll also say that a node corresponds to a clade if that node has those tips and only those tips as its descendant. So here on the left, we have a node labeled AB, and we see that it has tips A and B as its descendants. Now, we can uniquely specify a tree as a set of clades, being the set of clades that are represented here in the nodes. So as a set of clades, this tree would be represented as ABCD, AB, and CD as labeled in the nodes. And here's another familiar concept from Eric's talk. We define a subsplit as a pair of clades, and we say that a node corresponds to a subsplit if its children correspond to the subsplit's clades. So here at the top, we see the node labeled AB splitting from CD, and we see its children have descendants AB on the left and CD on the right. So we see that this node splits the tree into sort of two sides that have AB on one side and CD on the other. And we can also represent this tree uniquely as a set of subsplits. Again, just making a set out of the contents of the node labeling. So this would be AB splitting from CD, etc., etc. So this lets us get back to the motivation of being able to prune trees and also being able to put them back together. So it's easy to prune a tree if we take this tree in the middle on A, B, C, and D as our tips. If we prune out tip D, we lose tip D and we lose the node right above it, and we end up with this tree on the left on tips A, B, and C. If instead we pruned out tip B, we'd lose tip B and we'd trim out the node right above that, giving us this tree on the right labeled ACD. Now, going backwards, the interesting part is quite a bit harder, but we can still do our best. So it's relatively easy if we started with A, B, and C over here and our tree on ACD over here. We'd need to take one tip from one side and add it back into the other. So if we wanted to add tip D back to this tree on the left, we would see that tip D is above tips A and C and their ancestor. So we would need to find that common ancestor of A and C and put tip D attached to a node above that. And that's a lot of words to describe that we get this middle tree back in the middle. If we go the other way, we need to insert tip B back into this tree on the right. We see that we need to insert tip B between A and C, but closer to A. We find that there is a compatible spot to put that structure in, and we get this tree in the middle. Now, frequently, the exercise won't be as simple as that, and there may be ambiguities. You may get multiple trees that are compatible with your starting more pruned trees. And you may find that there are incompatibilities. You may get no trees at all. So there's another extension we can make. Instead, what if we started with fragments from many trees and we wanted to put together many trees that restrict to what we see in the restricted space, the pruned space? And this is where it gets a little bit more complicated. So to help with that, we need to draw on this concept of a tree distribution. And for that, we'll define that as a probability distribution on tree topologies for a given tip set. And we'll need to keep track of each tree in a distribution that has a positive probability. And we call that the tree support. So our exercise basically boils down to this sort of diagram here. So we take a tree distribution on this tip set on the left, this tree distribution with this tip set on the right, and notice that many of their tips are shared. The tips in purple are shared in common. And we wish to create a tree distribution using information from both of those that is on all of the tips, but still reflects the information from our source or reference distributions. So all of this falls under the research umbrella of supertree analysis. And we can do a search and we see that this is a large and active area of research, but it's primarily focused on this sort of single tree exercise of creating the best tree that reflects the information you have from the different tip sets. There's not as much activity in this field in a Bayesian context. There's a number of different articles at the moment, but it's mostly a handful. And I feel like the primary example would be the Ronquist paper in the last few years. But it would be very useful to have more focus on the Bayesian supertree context, because Bayesian inference is expensive, and it would be great to have information from our source distributions and being able to put it in without having to restart the Bayesian inference from scratch. So the reason why this is a less active field is that it is a hard problem, but we can simplify the problem somewhat by taking a variational Bayesian approach, and this will be very familiar from Eric's talk. We can supply a variational distribution that has handy-dandy properties, and that has useful properties for our ability to infer its parameters. So once again, we'll talk about this idea of subsplit Bayesian networks. So in words, we say that each tree node, we can ask what subsplit is likely to correspond to that node given its parent subsplit. So for instance, if our node's parent corresponds to subsplit ABC splitting from DE, how often does our node correspond to subsplit AB splitting from C? So if we have enough of these conditional probabilities that there's no possibility of reaching a dead end and having no distribution to make our way to the tips, we refer to this as a complete distribution and call it a subsplit Bayesian network, or an SBN. And for the rest of this talk, we'll use a shorthand. We'll refer to a child subsplit and its parent subsplit together as a parent-child subsplit pair. And we'll refer to the set of PCSPs with positive probability as the SBN's PCSP support. Now, it's quite easy to train an SBN to match a posterior sample like the output from BEAST. It's often as simple as counting up the number of times a particular PCSP shows up in the MCMC output, the posterior sample, and then divide by the number of times that the parent shows up in the posterior sample. And we found that this training of the SBN does excellent work in approximating the posterior distribution. Now, returning to this concept of restricting and combining these distributions, it's easy to restrict an SBN onto a subset of its tips. So, sort of summing up our objective, if we're given a set of reference distributions, often SBNs themselves, and they'll each have their own tip sets, we can try to find a supertree SBN on the combined tip set, such that if we restrict it to a particular tip set, it'll approximate its corresponding reference distribution. Now, we'll draw here on a concept called KL divergence, which is a standard way of measuring the differences between probability distributions. It has handy properties, including a very clean gradient with respect to its continuous parameters. And we'll be optimizing our supertree distribution by minimizing our supertree loss function as listed here. Now, this will just be the sum of the KL divergences between each of the reference distributions and the restriction of our supertree SBN to the appropriate tip set. And we have the nice property that when the references themselves are SBNs, we can calculate the gradient of this loss function in quadratic time with respect to the size of the supertree PCSP support. Now, you would be right to ask, how do we know what the supertree PCSP support is? Would we have to use every potential PCSP? And that would be somewhat impractically large. It's better than the tree support, which will be often very, very large. But if we don't have an intelligent way of finding a more circumspect PCSP support, we'll run into computation time issues. So we want to find a mutual support in an intelligent manner. So the way we approach that is we take the supports of our reference distributions and systematically construct a mutual PCSP support on the combined tip set. So the way we go about doing that is we recursively look for PCSPs that are compatible children of current elements of our mutual support that we've constructed so far, but elements that also restrict to elements present in their respective reference supports. So each element that we're putting into our mutual support has to restrict to an element in each of the reference supports. And we've proven a handy result that if the references cover the true support that we're trying to cover, then the mutual support will cover the true support on the combined tip set. So we know that as long as the references do a good enough job, this mutualized support will do a good enough job. So now we have all the building blocks to wrap this up into a workflow. So starting with either SBN reference distributions, or we train SBNs on our reference distributions like posterior samples or other items. We then find the mutual support by combining all of our references into a mutual support. Then we generate a starting SBN distribution. We can either use random conditional distributions or flat conditional distributions across our mutual support. And then we apply gradient descent to our iteratively improving supertree SBN until our loss function converges or goes below a desired threshold. Now, we want to try and show that this works. So we take a set of sequence data and divide it into 3 data sets. We take all of our tips and we sort of treat this as our ground truth. And we take all tips except an arbitrary tip A, and we take another set that's all tips except for another arbitrary tip B. We run BEAST on each of these data sets to get posterior tree samples. We treat the output from all tips as our ground truth, and we treat the output from our all tips except 1 distributions as our reference distributions. We train SBNs on each of these BEAST outputs, and we run our method, which we'll call vbsupertree, on the SBNs for our reference distributions, and we measure how well the output approximates the SBN for our ground truth. So we worked this through on simulated data. We simulated a genealogy tree from the coalescent with 40 tips and simulated a sequence alignment with 200 sites. And we see that our loss function descends rather rapidly across several orders of magnitude, looking good from our point of view running the algorithm. And then because we have access to the ground truth, we can calculate the KL divergence of our supertree distribution across the iterations and compare that to our ground truth. And we see a similar trajectory showing that the KL divergence versus the ground truth descends similarly across several orders of magnitude, even after 50 iterations. So that's a handy result there. And running it on real world data, we selected 30 well-differentiated sequences from the 1993 Egyptian HCV sequence dataset, as analyzed by Pybus and others, and went through the same workflow. So here again, we see that our supertree loss descends rather rapidly at first and converges towards the end. We sort of cut it off at 50 iterations still. We see that it descended across more than one order of magnitude across the supertree loss. And since again, we have access to the ground truth run, we see similarly that the KL versus the truth descends as well and goes down by over an order of magnitude and also descends to a KL divergence of under 1. So heading towards the future, one issue that shows up is that if our reference distributions are derived from posterior samples rather than full distributions, as frequently shows up with MCMC, Monte Carlo error may lead to the mutual support missing parts of the true support. So we may need to find a way to make our algorithm less strict, but still not go overboard, making the posterior support or the PCSP support impractically large. We also still need to finalize the API of the Python implementation, but that is getting close. And it will be handy for computational speed to offload all these repeated vectorizable operations to a C++ library that our group is making called libSBN. And we'd also like eventually to sort of formalize this supertree process as part of the workflow. I believe this figure showed up in Eric's talk, as part of an online approach of inferring these tree posteriors with one additional tip on each, and then merge using our supertree method to create a tree posterior on all of the tips. And that's sort of the eventual end goal there. So that's what I have for now, and I would like to send thanks to Eric Mattson and Fred Hutch Cancer Research Center for guidance and support. And I'd like to thank Cheng, Andy, and Song for all their wonderful collaborations, and I want to thank you all for listening to me today.
Thank you very much, Michael, and questions time, please. Let's see if we have any questions in the chat, or perhaps preferably through the audio.
I had a question if there's not one in the chat. Can't see the chat. So one of the... sorry, Barbara speaking from the Hobart Hub. So one of the frustrations I've had sometimes with Bayesian inference is that, so philosophically it seems it'd be nice to be able to use the posterior from one run of a Bayesian inference as your prior in a new run of Bayesian inference, which doesn't actually seem to be practically possible with a lot of the current methods. Is some of the things you're working on here going to be a way of getting around that?
I think that is the desired end goal in many ways, is to try that. Let me bring up. I think there is a sort of resonating idea with that in this sort of final end goal of taking previous posterior work here and wanting to build on that with additional data, ideally through efficient inference here, ideally in a sort of online sort of way. And my work sort of is a means of combining different posteriors together to form the sort of best posterior you can find that's compatible with all of them. In terms of being able to use the previous posteriors as a prior, I think that's an adjacent idea, and I think our group is working on that. But I think my particular work is sort of adjacent to that as sort of a next step in the workflow in my conception of the problem.
Cool. Thanks very much.
Do we have any other questions, please?
And I think I'm having a little bit of trouble seeing the chat at the moment. So audio is appreciated, or directing me to look at the chat.
Yeah, I think when you share the screen, that's what happens. But we'll pick. I'll pick up anything if I don't see anything in the chat. So yes, please use audio. That would be preferable. Okay.
I've got one more question. This is Nick Fountain-Jones from Hobart. You can't both you and Eric mentioned Mandev Gill et al.'s work kind of briefly on Online Beast. I was wondering if you could compare some of their work to your work broadly, if possible.
I don't know if Michael, if you've read that paper,
Not off the top of my head. I think
Okay.
I need to.
I'll grab that question then. Yeah. So that's helpful. I mean, I definitely think it's a great practical advance in the sense that Beast is a widely used program and that they're making a widely used program available, but it doesn't really strike at the core of the problem of like extending an existing posterior. And I mean, they're very clear about this in the paper. It eliminates the burden. You'll need to run your chain for a while to get samples. So it's definitely like an excellent practical advance, but it doesn't quite solve the problem.
Okay, thanks for that.
Yeah, thank you, Eric.
Okay, thanks. Thanks again, Michael, for your interesting talk, and perhaps let's have some more questions later on. We are covering some very, very interesting issues, very interesting ideas today. So it would be good to have more discussion on it during a session later on. So please give thanks to Mike again. Thank you very much for a wonderful talk.
Yeah, thank you for having me and for organizing.
Yeah, it's really fantastic to be able to connect with everyone today, and we have such an interesting range of talks and ideas, and I hope that this will sprout into some collaborations later on, because yeah, there are some definitely very interesting ideas from different parts of the world. To let me introduce you to the next speaker. So this time. That will be live lecture from Hobart. Nick Beaton from CSIRO in Hobart is going to give the next talk on the evolution of PASS. Thank you.
Just try and get on with the full screen thing. Is that it? Aha. All right, I think we're good. Does everyone see that? Everyone hear me okay?
We can.
We can.
I'm seeing thumbs up.
Yes.
Okay. So yeah, I'm Nick Beaton. I'm currently working at CSIRO. This is work I worked on a couple of years ago with Barbara and a few other colleagues here at University of Tasmania. So I'm not actually working on phylogenetics anymore. So this is going to be a very much a, I think to borrow from a previous talk, an executive summary. So I've forgotten most of whatever I knew about phylogenetics, so you know, forgive me if I'm a little bit vague in some of the details. This is very much the kind of overall talk on the work we've tried to publish over the last couple of years. So this is the evolution of PASS. So let's start with a really simple, easy to solve question by proving evolution. It's just, yeah, just a minor problem. Really okay?
I'm just trying to make the camera in the right spot. I'm so sorry.
Oh, is it pointing at a funny part of me or something?
Yes, it had a lag. I was adjusting it and it had much more of a lag.
I was wondering if everyone was laughing. I felt like there was a joke I wasn't getting. So yeah, so I'll continue on while the camera's moving around. So I like to think about this problem as how do we prove evolution's happening in a particular phylogenetic tree? And what better quote to use than Charles Darwin? It follows that any being, if it vary, however slightly, in any manner profitable to itself under the complex and sometimes varying conditions of life, will have a better chance of surviving and thus be naturally selected. I like to quote people smarter than me. So let's start with that. Survival of the fittest. So we have a bunch of species and we add some trait. Let's make it a binary trait because we want to make this as simple as possible. Simple assumptions, Occam's razor. And we'll change the species survival rate. So this trait makes a species more or less likely to survive over a period of time. Okay, that model's boring because everything dies. If you've just got survival and no birth term, then over time, species will just die off and then you'll end up presumably with nothing left. That's the absorbing state. So how do we fix that? Well, we can have a diversification rate of new species. Speciation is kind of important. And then we'll have a binary trait affect this too. Okay, it's still too simple because we're actually talking about evolution and evolution involves mutation. So let's allow species to transition from one trait to the other. Great, I think we've got enough now. We've just invented BISI. So the binary state speciation and extinction model developed by Madison et al. In 2007, really good paper. And it's got 6 parameters. So we can use this model to give the probability of a known tree based on the extinction rate of a species-like trait, the speciation rate and the transition rate, just as I mentioned. So, and because it's the probability of a known tree, that means we have the likelihood of these parameters given a tree. We can do stats to it, trademark pending, take that creationist, we've just proved evolution, bam. So, looking good so far. I told you this would be an executive summary. So, all saying nice and easy, but of course it's never quite that straightforward as we've been hearing earlier in this session. We just have to solve these pesky ODEs. So it's a set of 4 coupled ODEs, and we have to do that over every branch of the tree. So the 4 parameters, like I said, I'm not going to go into details, but we have extinction parameters. So that's looking at the probability of extinction as time goes on over a branch. These ODEs are integrated backwards in time. So that's the E0 and E1, the first 2 terms. And once you have those, you can then plug those into these other ones, which are actually the, hang on, do I have a cursor? There we go. These other 2 ODEs, which actually talk directly to the probability of a tree, of there being, at that point, the species being in state 0 or state 1, so in either of those traits. So these ODEs solve that, but we have to solve them all the way along the tree. So I've drawn a very simplistic diagram here. So say you have, at the present time, blue is one trait and red is the other. We can do ancestral state reconstruction, so we can try and work out probabilities of what traits likely to be in ancestral species and go right all the way back to the root. So I should mention that all of this obviously assumes that you have a known tree. So this is a very different problem to earlier on in this session. A much nicer problem to have, probably. So, okay, we have to do numerical integration. That's slow. And if we've got large trees, which we often like to do, if we possibly manage it, the branches are often very small in kind of relative speaking, and the branches are often of varying sizes. So you have some interesting numerical problems, and it's not the most complex set of ODEs in the world, but it's not the least complex either. It's certainly non-linear. There's certainly a lot going on. So we came into this going, we want to be able to do this really large trees. It's slow. We want to do cool stuff. Maybe we might, at the end of the day, want to do Bayesian stuff. So MCMC or something a bit more sophisticated. So we use a bit of perturbation theory. We said, okay, let's assume that we're looking at small time, and instead of just doing the kind of the traditional numerical method of using like an Euler method or Runge-Kutta or something like that, let's actually try and use the forms of those equations and see if we can get a bit of extra value out of it. And you end up getting these estimated solutions over small timescales, which involve a couple of exponential functions. for the E0 and E1, as we mentioned before. And it turns out this speeds things up quite a lot. And we gave this method the name PASSE, the perturbation approximation of state-based speciation and extinction, which is of course entirely logical and not just because we wanted to make a cool tongue-in-cheek acronym. The accent was what was for fun though. So it worked pretty well. We found that it performs up to 50 times faster than traditional BISI if you kind of tune things nicely. It does have a cost of accuracy, but when we look at a particular problem of detecting selection effects, so we use like a log likelihood ratio test to see if we can show, or hypothesis testing, so frequentist, sorry, if you can show that mu naught isn't equal to mu1 or lambda naught isn't equal to lambda 1, so there's some difference in the speciation rate or the extinction rate. We can still detect that most of the time BISI can when we looked across a range of the parameter space. So we thought, this is looking pretty good. So we sent it off to systematic biology with hope in our hearts. And you can just tell what's going to happen in the next slide. We were rejected. But there is a good reason for that. Because just before we submitted this paper, we found this new method called Castor, which achieved a 12 times speed up, not quite as fast as BISI, but the important thing was it was an exact method. There was no loss of accuracy. So it was it's a very good paper. So I'm not bitter at all, not even slightly. But it is a very good paper worth looking up. So the reviewers kind of predictably and very understandably said, look, anything we can do with PASSE, we can probably do with Castor, and we're not going to have that accuracy problem. So it's not really enough. Okay, fair enough. What do we do now? So when we submitted this paper, we kind of didn't have time to look into detail at this model. We kind of went, okay, that looks pretty good. We better cite that. But after we were rejected, I kind of had a chance to read through the paper and try to understand a little bit better. And they rely on this concept they call the flow of the differential equations, which I find very relaxing. It made me feel a lot more relaxed, especially after having a paper rejected. It was nice to think about flow. It's very zen. And so my background is as an applied mathematician, and I kind of, I've done a lot of nonlinear dynamics and stuff, and I was like, I haven't heard of this stuff. This sounds interesting. So I looked it up, and and I'm terrible at explaining it, so sorry about this. But the basis idea is if you've got some linear system, and it doesn't have to be non-homogeneous in time, you can have some linear system, like so we've got this vector valued, this vector x, and we're looking how it changes in time. It's linearly dependent on that value, but we've got this matrix which is time inhomogeneous, so we've got some interesting time-dependent stuff going on, but it is linear. If we have this system and we've got a solution for it with a given initial condition, we can find the solution with any other initial condition by using a simple linear transformation. And that's something I've never really thought about before. But in this particular case in particular, it's really, really useful. Because instead of having to integrate over every branch of the tree, and unfortunately this little tiny tree example is not very good because, if you imagine a tree with 10,000 or 100,000 species and all these tiny little branches between all these different speciation branches, that's a lot of branches to integrate over. Instead of doing that, we can now integrate once over the whole tree, well actually twice, but it's a lot faster because we're not duplicating work anymore. Instead of having to run the ODEs over the same time period over and over again for different species, we use the same solution and say, okay, we're running it over here now in this different part of the tree for this different species. The initial condition's different, but what's happening in time is still the same. So we just use that linear transformation to update those results instead of having to numerically integrate again. So really useful, and like when I kind of realised what they'd done in this paper, I was amazed because it's kind of one of those things like, I wish I'd thought of that. So I actually took inspiration from one of Julia's previous Philomania talks, where she just filled it with memes. I just thought that's a really good idea. So thank you. So one of the great things about this method is it also works with PASSE. Our approximation is looking at small time steps. So instead of approximating against each branch a bunch of times, which is what I was doing before, we're now just doing those approximations across the whole tree. So whereas before, my previous method, I was maybe doing 10 or 20 time steps across each branch in the tree, we're doing more time steps now, but we're doing it across the whole tree, so we're only doing it once. So instead of doing maybe 10 time steps across 10,000 branches or however many you have, we're doing maybe a few thousand all up. And one advantage of this is instead of having to, so my previous method I was having to look at differentiating between those different branches where they were in the tree. So how I separated in the previous iteration of PASSE was looking at extant branches, so branches that ended in a species that exists in the current day versus things early in the tree towards ancient history. We don't have to do that anymore. We've just got this one time frame across from the present back to the root of the tree. So we can use adaptive time steps, which is a fairly, anyone who's done numerical methods before knows about this, and there's lots of different methods and you can play around with it. So we can keep that small time approximation, which is what makes PASSE work. So I was pretty excited about this. I thought, yes, if we can get that 50 times approximation, like 50 times speed up that PASSE has, and multiply that by the 12 times the speed up that Castor has, we can power up. Dragon Ball Z references, etc. But it's even better than that. It turns out, this I should say before I get too excited, this is very preliminary stuff. This is basically stuff where we went, oh, this worked pretty well. Let's go begging back to the editors of Systematic Biology and say, please, please let us resubmit because we found this actually works really well. So it seems to be, in preliminary analysis, that PASSE and Castor are actually greater than the sum of their parts. So when I haven't added this result here, but if you just look at a single run of a likelihood for a particular phylogenetic tree, PASSE added to Castor adds about 10 times speed, which is still good. You don't argue about an order of magnitude speed up. That's, I was pretty happy with that to start with. But then I thought, okay, well, what we really care about in this particular case, we get to do the I love those wrestling memes from the previous talk. We get to do the wrestling meme and do some maximum likelihood estimation. And we find when we do maximum likelihood, things get a lot faster again. And we actually end up being about 160 times faster than Castor, which multiplied by that 12 makes it about 2,000 times faster than the original implementation of BISI in the diversity package, for those of you who use it a lot. And I won't go into the details, as I said, executive summary, but the idea is that with Castor, and we replicated their method, they use gradient descent to find the maximum likelihood, and they use a few different kind of intelligently chosen initial conditions, randomly chosen in space. And Castor's range of maximum log likelihoods are about here. And the different approaches, so I used some adaptive time splits, some naive time splits, and the kind of rough best approach, which was ended up being 160 times faster, was probably towards the lower end of the range of Castor results, but still within that range. So it wasn't noticeably worse than what they did. And why is maximum likelihood a lot better using PASSE than just for a single run? Our guess at the moment is probably just because we're using the approximation, we're making the likelihood surface a little bit smoother, which probably makes maximum likelihood that little bit quicker. The kind of open question there, of course, is making that maximum likelihood smoother going to make our results more wrong, or is it actually just a nice little regularization thing that we've done accidentally and we've actually happened to hit a sweet spot? We don't know that for sure, but based on the Zanig tree of angiosperms, I think, I'm not a botanist, but it's got 34 odd thousand species, and using that tree, it certainly didn't seem to perform any worse. So that's promising results, even if only preliminary. So we're very happy with that. So because it's 2020, I sent these preliminary results back to Systematic Biology. I never heard back, and I would have followed up, but it's been 2020. It's been a hell of a year, as all of you know. So, and obviously I'm not a phylogeneticist anymore, so I've been kind of sidetracked on other stuff. But yeah, I think it's been pretty exciting so far that maybe we can get this thing published there or elsewhere, and hopefully we will do that soon. So yeah, thanks very much for listening, and yeah, any questions, feel absolutely free. Thank you.
Thank you very much, Nick. I'll open this time to questions. I have a question myself too, but let's start with questions from others. So if you could use audio, please, just jump in.
Nick, you got a couple of suggestions in the chat for new names from Yaoban and
Oh, no.
Joe. That Pastor was Yaoban's suggestion.
Oh, Pastor, I like that.
And Joe Felsenstein came back with Kasse.
Kasse. It still sounds fancy, which is the important thing. What's the C stand for? Is it Kasse?
Well, Pasta and Pasta.
Oh, right. Yeah, that could work. I like that. I thought Passe was pretty good, but you know, if the people have spoken, then.
But it is. I mean, now that it's 2,000
Passe
times
become
faster, it is
passe.
Passe.
That's half the fun.
Yeah.
So I thought all the SSE names in these methods were becoming passe, so I thought it was a self-referential thing, but maybe my humour's too sophisticated. I don't know. Well, not sophisticated enough.
Well, that's
Can I
the main thing
interject?
Sorry?
Okay.
Could I interject with a quick question?
Okay.
This is
Go.
Joe. Joe, does all this wonderful speed up also help non-speciation ordinary maximum likelihood tree inference?
Non-speciation, hang on, I have to parse that. So, presumably, yeah, I've kind of been looking at the one particular problem, but yeah, but presumably it should. I shouldn't see. I can't see why it wouldn't. Is this so trying to work the other direction, trying to like look at different trees? Do you mean, or?
I was just wondering whether maybe in the ordinary ML tree inference, we had already analytically solved the things that you are having trouble with.
I think I'm like I said, I haven't worked with this stuff for a couple of years, so.
Did you want to make a comment, Barbara? You were looking poised.
I guess in standard likelihood you don't have differential equations turning up that you need to solve traditionally, do you? So I don't know what the broader applicability of it would be just for sort of standard likelihood, but worth thinking about maybe. Yeah.
So more of a comment. This is Mike Charleston in also Hobart. I'm intrigued by the idea of this sort of have you smoothed out the landscape too much kind of question, or your likelihood landscape, or is it, you know, the right sweet spot of between smoothing it so you have a very fast convergence and smoothing it too much so you actually get the likelihood calculation too far off. So it'd be interesting to try and find, first of all, whether you can even define what that sweet spot is, and then where you're near it or too far away, or how to find such a sweet spot in the future. So just to
we've had some discussions about that in terms of recently using it, and we're kind of torn between. It'd be nice to really honour that problem, and it'd be nice to get this thing out.
Yeah.
So, but like, it's an interesting problem, and yeah, we've certainly done. It certainly looks good for that one tree that we've looked at, but obviously that's not a general case.
If I may, I have also a comment and a question, I guess. So that the BC model that you mentioned is a special case of a Markovian binary tree discussed by Nectarias Conteleon in his 2006 PhD thesis, which itself is a special case of quasi-birth and death process introduced some years later, earlier, also a special case of branching process introduced, I think, in the 70s. So there are those various connections to other models existing earlier on. In my talk, I'll go into details later on Friday, but I'm just wondering, because for example, there are differential equations for the MBT model, which are sort of more general than the one that you presented today for the BC model. So in that sense, those are special case. So I'm just wondering whether, sorry, there's some noise. So I'm wondering whether there might be some interesting ideas coming from that to apply to those more general models. So yeah, I think it would be good to explore. Have you considered that?
Yes, I don't know about those particular models you're talking about, but certainly like a lot of the SSE stable, both Castor and BISI would be applicable to those. I think there's a couple of particularly complicated SSE models that might be a bit more tricky to implement, but certainly like Musi and Quasi and possibly Sexy, I think as well. There's a few, and I think it works well for most of them. It's just a matter of whether the ODE has that similar form, and if it does, it's pretty amenable.
Yeah, so yeah, I would be very interesting to hear your opinion on that, because for the more general model, called Markovian binary tree models, we do have differential equations that are in a matrix form. But yeah, it would be very interesting to see whether you would be able to solve those problems quicker.
Yeah, I'll have to pay close attention to your talk and have a look at the ODEs and see if I can work it out. But it's, yeah, I'd imagine probably.
Okay, all right. Thank you very much. Thanks again, Nick, for your talk. Thank you. And we do have discussion session starting now. And can we start with summaries from the two speakers that have recorded talks, pre-recorded talks. So can I introduce you to Sung Kwang Jun from Fred Hutchinson Center Research Center? Can we connect with you? If you could give us a summary of sort of key ideas from your pre-recorded talk.
Yeah, so thank you. So my talk is joint work with Hassan Nassif and Eric Masson. So this project started with a question. So we are wondering, to what extent can we marginalize out the trees in phylogenetic inference, and what can we gain if we can? And so obviously marginalization over all topologies is infeasible. So we use this subsplit representation proposed in Zhang and Masson, and that Eric and Michael also touched upon in the previous talks. So this lets us limit the number of trees to sort of like the core interesting subset. And this subsplit representation has shown to perform well in capturing the posterior distributions through a series of experiments conducted in Zhang and Masson's 2018 and 19 papers. So building on this, we basically develop a dynamic programming algorithm where so we call it generalized pruning algorithm because there's flavor that, so basically it extends Felsenstein's pruning algorithm to multiple trees. So this is a two-pass algorithm over a directed acyclic graph that encapsulates all the trees spanned by the subsplit. And it can compute exact marginal for a single site. And we basically combine them to form composite likelihood function. And we basically use this as an objective function to optimize the branch lengths and the subsplit parameters. And yeah, so in the talk, I also show some experimental results showing that it performs well. And I highlight the fact that it's very fast. So we worked with Ebola virus data involving 1,500 sequences, and it converged in an hour. So yeah, so it seems to be, so one of the goals was to do things fast, and it certainly seems to satisfy that goal. So this is still an ongoing work, and we are trying to explore further possibilities of using composite likelihood, like in expectation maximization framework or other frameworks to sort of see how far we can go with this. That's it. Thank you.
Yeah, thank you very much. I'll open this time to maybe a couple of questions to you before we move to the next speaker, and then we have a general discussion. So if you have any questions at this point, please use audio, just jump in.
I have a question for Jun. To me, it's very clear that the work going on in the lab there is very much centered around trying to make sort of inference a little bit more transferable. I think your talk in particular is hardest for me to see how that fits in, right? So I was hoping you could comment a little bit about the synergy between your work and the other work of the presenters from your work from your lab here today.
Yeah, so that's a good question. So I guess my project is it's a little bit specialized, I guess. So the variation of doing, so this subsplit representation of the trees lets you do variation inference, and it's sort of like a different way of doing Bayesian statistics. My method is sort of like thinking like, okay, so what if we, like, can we not sample? Because even when you do variation inference, you still have to sample trees and compute a gradient over the sample trees. So we're thinking, okay, what can we eliminate this, you know, the stochasticity coming from the sampling steps? So it's sort of trying to remove one source of noise and see if we can still estimate parameters. And that's sort of how it ties in with the rest of the work in the book.
Thank you.
Thanks.
Thank you. No further questions at this point. Okay, let's perhaps move to the next speaker, Matthew Foreman from University of Technology, Sydney. If you could please give us some summary overview of your talk before we go to questions, please.
All right. Hi, thank you for having me. I'm very happy to be here again. That's the third time I present my work on variation inference. And every time I was the only one, and this time there's 4 talks about variation inference. So it's nice to see it catching on.
Can't hear very well.
Eric did a good job at presenting variation inference. So I don't have much to say, I think. But to recapitulate, we try to do variation inference because we think MCMC is a bit slow and it doesn't scale very well with large data sets. Something like more than 1,000 sequences is very hard, for example. Unlike MCMC, it's based on optimization instead of sampling. So that's a major difference. The biggest problem I would say with the MCMC is to have a very good proposal, especially if you want to sample trees, like topologies. For variation inference, we don't have this problem, but the problem is to have a very flexible variational distribution. So usually it's just independent normal distributions, and that's it. So now the goal is to have a more flexible distribution that can take into account correlation between parameters. So that's the biggest problem with variation. In phylogenetics, you need to be able to take the derivative with respect to every parameter in your model, in your joint distribution. So that's one requirement. I remember Peter Bailey talked about this issue. So that's one of the requirements. And it can be very slow to do that. And so now we're doing a library that can do this very efficiently. And I talk about this in my talk. So now we take derivative by hand. And so it's much faster than automatic differentiation. I'll talk a little bit about this. What else? Eric said we can do anything we want with variation inference, unlike MCMC. MCMC, you can't cut corners, but in variation inference, it's kind of easy. And that's what we're trying to do now, is to cut corner, but at least it's going to be efficient. And hopefully it's going to be as good as MCMC, and then it can scale to big data sets. My work is mostly in I don't worry too much about topologies. Eric likes it, and Michael and Song too. But I mostly think about the continuous parameters. So my life is a bit easier than theirs. But now we're working together so we can have discrete and continuous parameters inferred at the same time. And yeah, that's probably the next 5 years of my life. I'm going to work on this, and it's very exciting. The goal is to do then online inference. That's a big part of my work now. With Eric, we did some work on SMCs, sequential Monte Carlos, to update distributions. And now we're trying to get variational inference and sequential Monte Carlo together to do everything at the same time, so it works. Might be unusual, but I might comment on the question Michael got about Beast doing online inference, because they wanted to compare Beast to his work. I know a little bit more about Beast, not too much about Michael's work, but in Beast, they just try to restart the MCMC where they stopped, and then they just add a sequence. So it's just discarding all the samples from before. It's just using the last sample, update it, and do MCMC. In what we're trying to do, and what Michael is trying to do, we try to update the whole sample you get from MCMC. So if you've got 10,000 sequences, 10,000 samples, you want to update every 10,000 sample. In Beast Online, they just use the last sample. But we're trying to use Beast to update everything at the same time. So this is work I work with Andrew Rambo and Mark Suchard and Eric on this. Yeah, that's it for me. If you have any questions.
Thank you very much. Thanks for overview of your talk and also ideas. And let me open this time to questions from the audience on any of the ideas, topics we have covered today. So as always, just jump in, use the audio preferably. If you can't, then type, and we'll have a look in the chat as well. Okay, I'm not sure whether there is a question from Martha or an attempt. Sorry, we can't hear you. Okay. Okay, right. So we do have a little bit of time before the break. So perhaps do we have any questions from the audience in the lecture theatre at University of Tasmania?
Very cool. You can read some papers.
Everybody's busy. Reading. I actually have a. Can I have a question to Nick again? Because sort of trying to understand what you are doing. Can you just reiterate again? Apologies for asking again. Sort of. The authors of the paper on the BC model, they derived some differential equations, right, which they are trying to solve. And your approach is different in what particular way?
So we're solving the same we're solving the same ODEs, but what we're trying to do is just approximate that to make it faster. So whereas the Castor method was good in that it solved the problem exactly, we're trying to say, well, okay, yeah, we might be able to get away with a little bit of error if we can speed this process up. So it's kind of using the maths to make a kind of, I don't know, more intelligent numerical scheme, I guess. It might be the best way to think about it.
So that's I think that's interesting, and the reason why is so there are those various differential equations in the theory of MBTs, Markovian binary trees, and sometimes there are issues with instability, some of those equations actually were understood. So for example, differential equations for ET quantity, so probability of extinction, these actually were understood, so they work well. There are some really fast algorithms for extinction probability under MBT model, which is more general than BC or MUSI model. But there are some other equations that, or even those that like we have recently derived, and I'll talk about about this on Friday. But there are definitely, as far as solving differential equations, there can often be issues with instability depending on the parameters of the model, and so other approaches are often sought. So yeah, I would be interested to hear what you would have to say on those once you have a look at those, I guess, more general differential equations or differential equations for other quantities similar. Okay, thank you.
I'll just comment to that. Sorry, the original paper we did try to explore parameter space, so across those 6 parameters of BISI, and you do see differential performance not just in our approach, but also in the BISI numerical model itself, and how quickly you can solve those things. And so obviously things like when you have a tree that's has an extinction rate and a speciation rate quite close to each other, then things can slow down quite considerably. So you do have those kind of issues, and I think stability around those wouldn't surprise me if there were issues there.
Okay, thank you.
I've got another general question for the variational inference folk. Like I do lots of bigeography using BEAST. Is there any plans in the future to incorporate biogeographic models into all this? Or
if you don't mind me grabbing this one, yes, but it's hard, right? I mean, I think my goal for the next decade is to make something analogous to Mr. Bayes. But then let's talk about BEAST. But I mean, I should say, like, Matthew's work is more on the BEAST side of things, but I don't think we've thought so much about state models yet. But remember, like, BEAST came out significantly after the first papers on Bayesian phylogenetic inference. So give us a little bit of lag time. But there's nothing inherently there that shouldn't be blocking it, right? So the types of trees that BEAST uses are trees with additional information at the internal nodes. So here we need to be using equivalent sorts of structures where you have substructures with extra information at the internal nodes, if that makes any sense. So there's no reason why we shouldn't be able to do it, but it will require from scratch rewrite. And I think that there's a cool opportunity to think, like, what is the very, very general form of what we are actually doing inference on, and how can we extend inference to that very general state space? Matthew, do you have anything to say?
I've tried to use variational inference in phylogeography, but it was way too slow. I used it for COVID, but the matrices were huge, so like 70 by 70. And yeah, it was very slow. Too many parameters on a fixed topology, of course, for me. But yeah, there's nothing impossible. It needs to be done.
yeah, thanks for that.
I also, I have a question. I'm very interested in because there are those various sort of different approaches to, I guess, modeling a tree, and For example, if you assume a particular model, like for example Markovian binary tree model, then with a small number of parameters, you can get a wide range of behaviors. So the number of parameters can be quite small. Then on the other hand, if I understand well your talk, Eric, I think you were talking about conditional probabilities corresponding to a particular structures, to particular topologies, rather than particular models of evolution. And so I'm wondering, in terms of, I guess, complexity of parameters, the number of parameters, the set space of parameters, I'm just wondering whether having like a difference between having a model with a smaller number of parameters versus sort of general structure based on data where you just talk about perhaps certain probabilities of certain structure. What is, I'm just wondering what is more efficient? Do we have an experience on that, like as a larger community, I guess, as a group of researchers doing work in various areas? I'm just wondering about that. Eric, can you comment on that?
I guess, I mean, there's two different things I think that we're talking about. And one is probability distributions on evolutionary processes as distinct from a given data set. That's, I think, the sort of macroevolutionary models. We're talking about something slightly different, which is, let's think about the posterior distribution on trees for a specific data set. And they're very intertwined, but they are distinct. So, I mean, I'm more experienced in the types of models that you have in Beast or something like that, where there are parameters for a macroevolutionary model that you get sampled in conjunction with the posterior distribution on that specific set of trees. But again, they're sort of two different sets of parameters.
I think that might be a natural place to end the discussion, unless anyone has anything more pressing. So I'll just stop the recording somehow.